So anyway, binomial distributions, it turns out that there is so well ordered that we can calculate the mean and standard deviation theoretically. There's a little calculation for that. And I don't expect you to know this, but if n is the sample size, and little p is a probability of an outcome, one of the outcomes, I know my board's getting a little messy here. For example, we're flipping a coin, p, if we say that's the probability of flipping a heads, p would be 0.50 or 50%. Then it turns out that the population mean for a binomial distribution is the sample size times this probability of one of the two outcomes. And the standard deviation, and notice I'm using the Greek letters because these are population standard deviations. The standard deviation is the square root of np1 minus p. So I don't expect you to learn this. Don't worry about it. But if you're curious, I think it's kind of neat that we don't have to look at binomial outcomes and calculate a standard deviation. We can calculate it theoretically through these types of formulas. And what happens is you end up seeing things similar to this in the formulas that we use coming up in chapters 6 and 7. So anyway, the binomial distribution, and I'm going to do a little bit of racing here so I have some room to play here. The binomial distribution is an example of a discrete probability density function or probability distribution function. So our discrete means that it's choppy. You know, I can't, for example, measure 1.2 heads or 3.7 heads. You know, in this case, it's just integers, discrete. Compare that to continuous. Continuous means smooth, which we'll see like in a bell curve. So there are two forms of probability distribution functions. There's discrete, there's also the continuous form. So in this book we work with a probability with the binomial distribution, but we do and we don't. It turns out, because we're using large samples, we actually don't work with this specifically. We work with the bell curve, the normal distribution. So let me give you an example of this. I have, some years back, I created a simulation of flipping coins. I wrote a computer program that simulated by generating random numbers the flipping of coins, and it runs very fast. So my experiment was this: flip 100 coins, count up the number of heads, record that number, and then repeat the experiment 10,000 times. So 100 coin flips, 10,000 times is flipping a coin 1,000,000 times. In the course of doing this, keep track of all the results and draw a histogram and print out all the probabilities. Okay, so how long do you think it took? How long do you think that takes? Well, last time I ran it some years ago, it took a couple of seconds. On my current laptop, it would probably take 1 or 2 seconds. Very fast. So flipping 1,000,000 coins. But, and this is on my website, and so my website, which I'll, if you're taking this course from me, I'll make that, give you the links to that, so you can. I've done 4 of these. Here's one of the simulations I ran, and flipping these 1,000,000 coins. So this is a bar graph, a histogram, very much like that, except there were a lot more different types of outcomes possible here. In this case, I think the top bar was 50 heads, 50 tails. I know I have another one where actually it came in, I think, 49 heads and 51 tails. It's a little unusual, but then it, you know, spaces out here, and the most extreme in this case was 31 heads and 69 tails. That happened one time out of 10,000 trials. Once out of 10,000 was 31 heads and 69 tails. The most extreme I ever saw was 25 heads, 75 tails. That was a 5 standard deviation outcome. Because the standard deviation for this experiment, using the calculation I erased, is 5. So 1 standard deviation is 5. In other words, 45 heads or 55 heads is 1 standard deviation above or below the mean. Alright, so, but what do you see here? We did this coin flip simulation, and it looks like a bell curve, doesn't it? And that's literally where the normal distribution or bell curve comes from. You have to put on your, you have to think about calculus in this sense. If you were to flip an unlimited number of coins infinitely many times and plot it out, it would literally turn into the normal distribution, the bell curve. And I've done that. I've derived the normal distribution literally by looking at that. And if you know some calculus, I got to tell you, it was a very difficult project, and very a lot of work involved in that. All right, so but that's the binomial distribution, which plays a pretty considerable role in our course in chapter 6 and 7. All right, now the book talks about some other kinds of distributions. There's one called the Poisson distribution on page 190. And I know I studied it as an undergraduate. I don't remember a whole lot about it. I'm not going to worry about it. There's another one called the hypergeometric distribution. I'm not sure I've ever seen that before. There are different forms of discrete distributions. Now, the continuous distributions, the most important one is the normal distribution. We've mentioned that before. So that's, I let my book get away from me. It's forward a few pages there. You'll find the normal distribution.